So welcome everybody. My name is Kazi Rygl from the Italian ALMA Regional Center located at the IRA Institute of INAF in Bologna. I have some problems changing this. Okay. So this is indeed, as Megan said, the second iTrain that we have on VLBI with ALMA. Last year we had the first part, which was an introduction to the millimeter VLBI science and what you can do when ALMA joins VLBI networks. We also discussed that the two VLBI networks that ALMA can join is the Global Millimeter VLBI Array, the GMVA, and the Event Horizon Telescope, the EHT. Furthermore, we discussed how you can prepare a millimeter VLBI proposal with ALMA. So today we are going to talk about accessing and calibrating ALMA VLBI data, so the data taken by the VLBI array that contains ALMA. I will start with a brief recap on phased ALMA data and what you find in the ALMA Science Archive. And then George will take it over and he will talk about how to find and how to obtain GMVA data. And then Micheal will take over and he will talk about obtaining EHT data and how to calibrate both GMVA and EHT data. So just as a recap, we all know that ALMA is an interferometer, but thanks to the ALMA phasing system, the 12-meter array can be phased up to form a large virtual single dish of 77 meters. As such, as phased ALMA, it can then participate to other VLBI networks. Since it's also the largest dish to participate to this network, so the most sensitive component. A bit more detail about the ALMA phasing system. So this system computes the phase adjustments for each antenna with respect to a reference antenna. After these phase adjustments have been implemented, and this is done in real time, all these antennas can then be summed together to create, in the ALMA correlator, the virtual sum antenna. If you want to know more details about this, please have a look to the publication of Matthews et al. 2018. So what kind of data is collected during phased ALMA observations? Of course, the 77 single dish data is correct. So this phased ALMA single dish is recorded and will then be sent to the VLBI correlator to be correlated with the other VLBI antennas. But at the same time as ALMA participates to VLBI observations, it also writes the interferometer data from these 12-meter antennas.
Kazi, I think you're muted now.
Thanks. Yeah, I had some problems with changing the slides, so sometimes I have to click. So this phased ALMA data also passes through quality assessment, as does all ALMA data. However, the main purpose of this quality assessment is a little bit different, and I will explain that a little bit more. So ALMA has linear polarization feeds, and when it records polarized signals, it will do so in X and Y polarization. The other VLBI antennas, they have circular polarization feeds, and when they record polarized signals, they record them as left and right. So then when phased ALMA is sent to the VLBI correlator and it's correlated with the other VLBI antennas, you get visibilities that are of a mixed polarization basis, as you can see on the bottom left here, this matrix. Now, these kind of visibilities are very difficult to calibrate. So what you would want is to have visibilities in a single polarization basis, namely the circular polarization basis, as you see on the right. So to get there, we use a program called PolConvert. And PolConvert needs the full polarization calibration tables of the phased ALMA data to do this conversion. So that is the main point of the quality assessment of phased ALMA data. The second point is, of course, also to deliver ALMA interferometry data to the ALMA Science Archive. And this is done on project-based datasets. I mentioned project-based because Actually, when ALMA observes in VLBI mode, also the observations are done a little bit differently. Normal ALMA interferometer observes really project-based. But when ALMA participates to VLBI arrays, it observes track-based. And each track may contain more than one project. As for example, in this graph, you see that track C contains 2 projects, but they might contain also up to 3 or 4 projects. These projects will share or may share calibrators. In particular, they may share the polarization calibrator to cover a wide range of parallactic angle. And this means that also the quality assessment is done track-based rather than project-based. And if you want to know more details about the quality assessment of phased ALMA observations, please have a look at the paper by Godi and collaborators from 2019. So where do the observed data go? First of all, they all go to the ALMA correlator, which will output the sum antenna, which will then be correlated with the VLBI in the VLBI correlator, and it outputs the interferometric data. The sum antenna will then be recorded on a Mark 6 recorder and will be sent to the haystack correlator if ALMA participated to the Event Horizon Telescope observations, which you see in the center, and the haystack correlator is located in the US. When ALMA participates to the Global Millimeter VLBI Array, the phased ALMA data are the sum antenna data are sent to the Bonn correlator located in Germany, which you see on the right. I will now, since my colleagues will talk about the VLBI network data, I will now continue talking about what happens with the ALMA-only data, the interferometer data taken during VLBI observations. So this will end up in the ALMA Science Archive. It's very easy to find this ALMA-only data taken during VLBI observations because it belongs to ALMA projects that have all the same project code, namely ending in point V. And there's not so many, so it's very easy to go through them. For each observation, you can then find the following products. There are the raw data, and you will find the calibration script with all the calibration tables from the QA2. So this will be, of course, applicable project-based just for this data set. Remember that this QA2 does a full polarization calibration. So among the image products that you can find are the multi-frequency full Stokes images, 1 per spectral window. So you have Stokes I, Q, U, and V. However, you do not have any spectral line cubes, so any spectral cubes. You don't have, there's also no combined continuum image. Furthermore, there are no calibrator images because the calibrator of one project may actually be the target of another project in the same track. Furthermore, these data are just like the regular ALMA data, public 1 year after delivery. However, here with delivery is meant a confirmed successful correlation at the VLBI correlator. So now I've left the official ALMA environment, and I wanted to bring you to this repository, which is called Vapola, because this is a nice, it offers complementary data to what you find in the ALMA Science Archive. So Vapola stands for VLBI AGN polarization data with ALMA, and it contains ALMA data from ALMA-only observations taken during VLBI observations. And it will have different, it's really a complementary repository to the ALMA Science Archive. At the moment, it's not yet public. It's going to be public within days. So when I put the slides online, I will place here the working link. So let's have a quick look at what is in this repository and how it's organized. So it's organized per source, per band, and per observing run. You see here an example for 3C273 with data taken in 2017. I see there's data in band 3 and in band 6. If you click open band 6, you see for the observing day of 6th of April, all this data available. In particular, you have, if you go to images and FITS files, which are over here, there is all the advanced polarization data products based on the four spectral windows. So you will have Stokes I, you have the linear polarization, circular polarization, linear polarization fraction, and polarization angle. You will have also the plots, so the PNG plots of some of those polarization products, plus the spectral index map and the rotation measure map. Furthermore, which I think is maybe one of the most important things in how this complements the ALMA Science Archive, you will have the calibrated visibilities without any channel smoothing. So if you are interested in any spectral behavior of these targets, the quickest thing to explore that would be to download these calibrated visibilities and make your own image cubes. So just to leave you with some examples from WAPOLA, here you see the plots from M87 in polarization. On top, you see the Stokes I image. And note that these are ALMA-only data taken in this compact configuration, right? So you see that the angular resolution is something between 1 and 2 arcsecond in band 6. So for M87, you see nicely the core and you see the jet and also the hotspot within the jet. On the bottom left, you can then see the polarization fraction and how this is changing across the jet. And on the right bottom, you see that there is even some circular polarization in the jet. Finally, there is here the plot of the rotation measure on the bottom left. So the rotation measure is the change of the polarization angle over wavelength squared. And on the right, you see the spectral index. And note that both of these are calculated across the 4 spectral windows of ALMA. So this is where I hand over to George to tell us about obtaining GMVA data.
I share quickly. I also just sent a link to my slides because it includes links to which are useful. Right, yeah, so hi everyone, I'm George and I'm the coordinator of the GMVA calibration here at the Max Planck Institute for Radio Astronomy. And I wanted to talk briefly about how to work with the GMVA today. So about the GMVA, it stands for the Global Millimeter VLBI Array. It has been observing at 3 millimeters for the past 20 years, I think, and very recently, last year, we also started offering 7 millimeters. With that, we can achieve resolutions down to 0.05 milliarc seconds, and the whole array consists of more than 20 telescopes, as you can see in the image, achieving supreme UV coverage. Specifically, we have going from east to west the 4 KVN stations in Korea. In Europe, we have 6 stations, 1 in Finland, 1 in Sweden. The Effelsberg 100-meter radio telescope that we operate here in Bonn, in Germany. NOEMA, of course, in France, and in Spain, there's the Yebes telescope and the IRAM 30-meter telescope. We have the GLT joining in Greenland, giving us the north-south resolution that is so important. Of course, the VLBA is also joining with its 10 antennas in the US. And then finally, APEX, the Atacama Pathfinder Experiment telescope, joined us last year, and we successfully found fringes to that. And with a green dot, of course, ALMA, the main focal point of the day, which, when is available, is usually the anchor station that we use for all kinds of things like fringe finding, correlation, calibration. The GMVA is an open sky instrument, so it's based on an MOU between observatories, which means that PIs can just submit proposals, and if it's accepted, they get the data. They don't need to worry about anything else. And ALMA, as we heard, joins as a phased array in the spring session only. So as of now, it joins once per year. So how do we obtain GMVA data? There's 2 ways to do that. As I mentioned, we can propose them. So if you want to do a proposal, then the first step you need to do is to go to the GMVA website. And in my slides, you can find the link to that. There you can find all the important technical information that you need to consider, like sensitivity of the telescopes, the angular resolution that you can achieve, and other important information for your proposals. Then when you have the idea for your proposal and you want to start writing and creating it, then we use the NRIO portal. So it's streamlined similar to the VLBA. You just use the NRIO website and just click that it's in fact a GMVA proposal, and you submit it the normal way. And then if it's accepted and observed, the final step before you get your data is to check our Decky page from the Max Planck, in which we create correlation reports, and you can check there if everything went well, if you need to expect that some data is missing or some stations had bad weather, where fringes were found. So in general, a lot of very useful information that you need for the calibration of the data. And of course, the alternative is you can just grab the existing data, which again you can find at the National Radio Astronomy Observatory's data portal. So in that case, you just either look for the source you're interested in, or if you know the project code, which again you can find on the GMVA website. So if you have the project code, you can just also put that into the search mask and retrieve what is available. We as the correlator team put the data when it's released to the public, which is 1 year after the data are provided to the PI. But if you don't find something or you're not sure how to get it, you can also contact us, and we can always get the data if it's publicly available for you from the tape archive that we have here, put it on the FTP server, and then you can just grab it. So some proposal relevant information. As I mentioned, there's a call for proposal issued 2 times per year, with the deadlines being in early February and early August. If you do want to include ALMA, then you need, of course, an extra proposal for ALMA. The way you do is you submit a GMVA proposal in early February. You cross your fingers that that gets accepted, and you also submit the ALMA one. And then if all goes well, then you get a positive reply from both the GMVA and ALMA, which means that your observations will then be scheduled for next year. And as I said, yeah, the proposals are streamlined within the NRAO proposal too. So usually the proposals, the accepted proposals are observed at least 1 year later, can be also longer if the PI requests that, if they want a specific session. We, the MPIFR team, prepare the schedules for all observations. So this is different, for example, compared to the EVN, where the PI needs to do that themselves. We take care of that. Then we correlate the data and share them with the PI. And we also provide limited support with regards to potential issues, which means we are always hopeful that when we do give the data to the PI, that they can quickly have a look, tell us if they identify any issues that might be there. And if that's quickly enough, so let's say around 6 months after, up to 6 months after we give them the data, we can still then maybe recorrelate something if it needs to be done. Because after that, we do delete the data to make some space, at least the raw data. Briefly to mention the bond correlator, the part that I'm working at. So you can see here the Mark 6 modules, slots on the left, and the module library on the top right, and the correlator itself at the bottom right. Some technical specifications of the correlator are that we have around 68 compute nodes, 1,360 cores, with a data storage of around 1,200 terabytes and 48 terabytes of correlated data storage space and 40 terabytes of backup. We have network speeds of around 56 gigabit per second using two-head node for correlation, and we're able to run multiple correlation jobs in parallel. We have a head node for other tasks and the 12 Mach 6 playback units and 14 Mach 5 units. And as a last slide, some GMVA highlights that I think are very cool. We had the first image of the black hole and jet connection in Rusa and Lu's paper, as you can see top left. We also had images of Sagittarius A star, you can see in the bottom left. And on the right, a source that's dear to me, 3C84, we were able to observe that source with the VLBA, the GMVA, and the EHT, and get a lot of insights from all these observations. And I think with that, I can pass it over to Micheal to tell us how to get the images by calibrating the data.
Okay, thank you. I'll see if I can also share that one. Okay. Yes, so my name is Micheal Jansen, and I'm an assistant professor at Radboud University in Nijmegen in the Netherlands. And I'll be talking about the following points. So first, how you can get public EHT data from our archive. Then how you can calibrate the GMVA data that George was just talking about, and how you can then calibrate EHT data. So that's a bit more involved, but in principle uses the same or similar steps than for the GMVA data. And those will mostly be, let's say, about the mechanics of how you can run these things, which steps you need to take. And then if there's time at the end, I'll also talk a bit about the details of how you can interpret the output of the pipeline and so on, but that's I'll only be able to touch upon this because it's a very involved topic. It touches upon VLBI data calibration in general, so I'll only give you, let's say, some broad strokes there if time permits. First, after George's nice talk about the GMVA, I had one slide here, an overview of what the EHT is and what it can do. I think most of you know this millimeter VLBI array for producing these beautiful, well, I think they're beautiful images of black holes. And of course, we also do a lot of AGN science. So George has also showed the results from 3C84. And this is the currently the stations we have in the array. Actually, even that is not fully up to date. KVN stations also now joined. They have 2 now with the 1 millimeter receiver. So this array is also actually continuously growing. But here you see actually most of the stations and the frequencies which we currently can, let's say, that we offer currently, which you can observe. These are at 214 and 228. So these are the receiver side bands, and then each of these are actually 4 gigahertz wide bands. So you, for example, you can get simultaneously 4 gigahertz band around 214 gigahertz and a 4 gigahertz band around 228 gigahertz. Or you can tune it to this 260 gigahertz range. And also now we recently, it was the first publications also on that. We can also now do 345 gigahertz, which is the highest frequency you can do with VLBI on the ground. And of course, that is really in this array only possible with phased ALMA. It's the central most sensitive station we have in the array. So these bands for ALMA, the equivalent ones so that we're using are ALMA band 6 and band 7. The highest resolution we can currently achieve with this is 15 microarc seconds. And the data is correlated in Bonn. It's the same correlator that also correlates GMVA data, and also at Haystack in the US. So I had one quick slide, just as a reminder. This was covered in the previous VLBI iTrain version 1, but just as a reminder how you can get EHT data as a PI. There we have, just go on this website, eventhorizontelescope.org. then under for astronomers, then you can go to proposals, and then it simply points you to the ALMA proposal cycle. So the EHT proposals, they are coupled to ALMA, so you can propose for phased ALMA observations as you would for GMVA. You can also propose it for EHT. So that's how you would get data as PI, but that's just a reminder. Now I'll talk about how you can get EHT data that is on our archive. So after a while, usually after 2 years after we finish the correlation, EHT data from an observing year becomes public and anyone can access that. So you will find it again on this Event Horizon Telescope website. Then you go to for astronomers, and then you go to EHT data products here. And then you find a list all of different releases that we do in the EHT. So you marked some examples. For example, you can have multi-wavelengths data from publication on multi-wavelengths campaign. You can have, when we publish a paper, we usually publish the fully final calibrated and heavily processed data together with it. So that's not what I'll be covering today. Also some imaging scripts and different kinds of things. The data that is interesting, I think, for the group here is the raw data that we publish. So the raw correlator output that you can take, you can download, you can run, talk about later, own your public calibration pipeline on it, and you can go from raw data to calibrated data to make your own images, do your own science, which sometimes, for example, you can't do with the calibrated data that we publish because that's too heavily edited, and maybe sometimes we remove polarization information and so on. And also, right now, for example, this is a screenshot I took some time ago. This only has the 2017 raw correlator output, but now there's also the 2018 correlator output on it. And tell you, for example, not all of that data in 2018 we've analyzed and ourselves and published, right? So even if we have some calibrated data from 2018, it's not all of it. If you want to have a look at, for example, 2018 Saturn star data, you need to go to the raw data because we didn't publish that yet. Okay, so let's have a closer look to this. So we usually host our this archival data on two servers, one on the ALMA Science archive and on Cybers. And I'll talk a bit about both because both have their advantages and disadvantages. And I'll tell you at the end the best strategy, what I would usually do, how you can get this data. So let's first look at this ALMA archive. So this is, Kazi showed you the very nice interface for the ALMA interferometric data. Now this is for the VLBI data, and this archive is, as you can see, it's rather simple, and sometimes it's a bit difficult to navigate, I think. So the top directory here, this is in all of the 2017 data. Then here you have the different projects. You can click on each project, and then you get all of these files. But as you see, so you have everything here, but from this web-based interface, it's not so easy to know what data you need. So we keep that in mind, that it's all there, and we'll come back to that later. But the strategy that I would propose is that you actually first look at the Cybers data portal, which looks like this. So there we have actually a nicely web-based interface, and you can nicely browse through all of the files, see what everything is there. You get your README file. So here you can really browse and see what's available. Problem here is that if you want to actually download any of the data, you need some special software to do this, and it's again a bit tricky. So that's, well, in the end, how you can best do this is combine both worlds. You use a Cybers one just to get an index of all of the files you want, but the actual download is easier to do from the ALMA server actually, because there you don't need the special software. But you can, of course, also go through these installation instructions and get your special software if you want. But okay, so let's again look at the overall Cybers data archive. So if you click on this link on the Event Horizon Telescope, you get overview like this. And there's one important file that you should look at. There's this inventory.txt file. So this is looks like this. And this is a small file. You can download it also without special software. And this tells you all of the files that are there in this archive. So we can look at it in a little bit more detail, and this then gives you also the structure and how the data is organized. And I'll talk about that now a little bit, what this means. So these first parts here, these project codes, and then this string here is not so important. What is important in all of these files, for most of you, I would assume, is this last part of the file names. So this E17, this means these are from EHT observation taken in 2017. And then next you have letter codes A, B, C, D, and then numbers. So these letter codes, these were Kazi also talked about, these are VLBI projects. So that's why we have a specific VLBI observation track of when which source is observed at which time. And these are then called just track A, B, C, and D, and so on. And these are executed on different times. And this year, this was observed in April. Sometimes we also observe in March. And then this means that, for example, D05, this was EHT or VLBI track D observed on April 5. Then if you have A10, this is, for example, track A observed on April 10. The 7 just means this went actually through 7 iterations of the correlator. That's also what George alluded to. Sometimes we need to rerun correlation because we need to fix issues. But once it's on this public server, then this is the final version of the correlator output where all issues are identified and correlation went fine. And then the next one is the frequency identifier. So in one of the first slides, I talked about different frequency tunings that we have with the EHT. In 2017, we only had 2 bands. So this is the low band and the high band. So low band was 226 to 228 gigahertz, high band 228 to 230 gigahertz. So we didn't use the full band. It was just one of the receiver side bands here. But that's then, there's essentially 2 different frequency coverages here for low and high bands. This is for 2017. In all of the following years, so 2018, 21, 22, and so on, this will look a bit different. Then we have band 1, 2, 3, and 4. And these are then also all 2 gigahertz bands that are, for example, then centered around 213, 215, 226, 227, and 229 gigahertz. And usually what you do is you pick for the calibration one of these frequency bands and you calibrate that separately, and then maybe take next frequency band, also calibrate that. And maybe if your imaging software can do it, then later on you can also, in imaging step, combine the calibrated data from these different frequencies to do, let's say, multi-frequency synthesis and these kind of things. Okay, and then the last, the remaining part of these files, then this is just says this belongs to the OJ27 project here, for example, and the actual source that's in this data is then here 1055-018. And you see there are also different types of files. So for example, you would need the forfeit output, or it's not shown here, there's also Mark IV output. This you would need if you want to run, say, a hops-based pipeline, but I'll be talking about here because it's also relevant for the ALMA community. Later on is a CASA-based calibration pipeline. And for that one, you only need these FITS files. These actually contain FITS IDI data. This is then the raw EHT visibilities from the correlator as the CASA-based pipeline can read them. And one other thing, Kazi also talked about this sometimes. So we have these different projects, and if you want to have all of the data, let's say on day from track D on April 5, you want to look at all of the projects because you can have multiple projects that were then scheduled also on the same day. So in this README, in this inventory.txt, you pick let's say your specific day you want to look at and the sources you want to look at and the frequency coverage, and then you look for them in all of the different project folders. So you have all of the data that you need. Okay, so let's say we have now made our selection of the files that we want from our inventory.txt file. So here, a very brief example. this would be, we want to have data on M87 and 3C279, only need this FITS extension, and all of them for the low frequency band and April 10 track A. Then we would have, for example, these three files here. And note, here you can see it already, they're two projects that have this data on the specific day of, both data on M87. So you won't really look in all of the projects. Then if we know, our selection of data from this inventory file that we got from Cybers, we can then do it easy. So just wget here, download from the ALMA Science portal. So you simply take, from inventory, you take these files, you can see them marked in red here, and you just add, the link to the ALMA Science portal at the front. So you just simply write a text file based on that, and then you run wget to get all of these files. This one gives you then all of the raw visibility data. If you want to run the full calibration, also including the amplitude calibration, you need some additional metadata. So this is untap tables that contain system temperature and gain information. This you also find, there's one for each project, and you just find it as this metadata file. So these are also easy to find in these inventory files. Just look for the metadata, and you can just download it either from the ALMA Science archive or also it's a small file directly from Cybers. If you, of course, life would be easy, everything would be consistent, but a few things to note here in terms of conventions. So if we first look at 2017, that data, we have these tracks A, B, C, D, and E. And then you have your metadata package, you have the untap files, and there you just see this capital A. So capital A then corresponds to track A10, capital B to B06, and so on. It's just something to be aware of. And in the metadata, also the files are labeled by sideband 1 and 2, that then in 2017 correspond to the low and high band that I talked about before. Right, so it's a slightly different naming convention between the visibility data and the metadata here. This is more consistent in 2018 and future years. There, you have sidebands B, 1, 2, 3, and 4, labeled both in the visibility data and also in these untap files, also have the same B, 1, 2, 3, and 4 labeling. And usually, so in these future years, in this metadata, you'll find an untap subfolder, and usually you want to have the processed ones that it already, let's say weird entries in the untaps removed. So you usually want to have these files. And one final word, again, if you want to look at the 2017 data, they quickly, each track, you will get two untap tables that are split for all of for ALMA only data for the ALMA station, for phased ALMA sensitivity, system temperatures, and so on, and all of the remaining EHT stations. So to run later on the pipeline, you just need to take those two files and combine them into one. But that's only for 2017. So that was the first part. How to get EHT archival data, and I thought, I'm not actually sure if we want to do it like this, but maybe if there are questions now, I could briefly stop and answer them right now.
Yeah, we can try that and edit the video. So you can either raise your hand or put questions in the chat.
I mean, maybe only urgent things for understanding.
Yeah, so I don't see anything.
Okay, then I'll just continue. There will still be time for question at the end. Right, so then, so this is now essentially you know how you can get your GMVA or your EHT data with phased ALMA. So now I'll talk a bit about how you can actually calibrate that. And as I said, first I'll go through, let's say, the mechanical steps, the commands you need to run to get the pipeline running that essentially goes all the way from your raw data and in the end gives you fully calibrated data that you can then run your imaging scripts on. And this is based on this CASA-based RPCard pipeline. can get it from this link here. So I think this is probably the most relevant one for the ALMA user base, because you're familiar with Kazi. I know that there's also another pipeline that you can also run, which is called EHT hops. So but that won't use the FITS IDI files, but the Mark IV data. First, a few general words about this pipeline. So it's published in this paper here, so you can read also the details there and also better understand what the pipeline is actually doing. So it's open source. You can just download it. You can also modify it. It's also fine. You can see it has a specific license that allows it. It uses Kazi's built-in MPI acceleration. So if you have a cluster, then you can have multiple cores running on it. The pipeline will make use of it. And it has all of the input and configuration files are simply set in simple text files. And the philosophy or the idea behind it is you initially only have to set very few basic parameters, essentially which sources you want to take as calibrators and which array you have. You set this quickly in your text-based input files. Then you just run the full pipeline, which gives you, again, goes all the way from the raw data to the calibrated data. And it produces a whole lot of diagnostics along the way that you can then inspect and look at to understand the quality of your data. And if with this default settings, everything works fine, or if there's specific issues, maybe with the bandpass or with some other calibration steps that you need to take care of, or some problematic data that needs to be flagged. So based on that, you would then say update your flag files or change some specific parameters in the pipeline. Actually, highly configurable. I think it has more than 150 parameters you can change there to deal with all kinds of weirdness you have in VLBI data. But for that, it is a pipeline. But if you want to encounter very problematic data that are not easily dealt with by flagging the data, it's still that you need a certain understanding of VLBI data to know what you're doing. Also, if you're fine-tuning this pipeline, and I will later describe how you can use it with phased ALMA plus GMVA/EHT data, but also know that in principle works for any VLBI array. So you can also use it for EVN data or the VLBA, for example. And essentially, what the pipeline is doing, except for, let's say, some tweaking and massaging and then already figuring out with some smart heuristics issues, common issues in your data. But apart from that, it only can boil it down to running just a simple series of steps and typical steps that is running for millimeter VLBI data. It's shown here. So first you load the data, you load your metadata, you apply some a priori flags to your data, then you do your amplitude calibrations, then you do a phase calibration of only your calibrator sources to get you all the way to all the instrumental corrections that you need to apply. So these are, say, phase offsets, delay offsets between your spectral windows, your complex bandpass, and right-left phase and delay offsets that can also be there between spectral windows. Then with those instrumental effects solved, so you just produce a bunch of Kazi calibration tables. Then you do a deep fringe fit with a deep search, and then optimized fringe fit solution interval later. If there's time, I'll talk about what it does in practice later. But this it then does on your science targets. And then in the end, it just essentially applies all the calibration to your data and produces additional diagnostic plots that you can expect to see how well did the calibration work. And then along this process, then it's easy that you can just, let's say, look at the calibration file. Oh, there may be issues with the bandpass. You tweak some settings there, and then using the same command line argument interface, which is this Picard command, you can just rerun any steps of the pipeline at any moment, and then update your calibration that way. And the input is just your FITS IDI data, metadata, and then the final output is calibrated and, depending on settings, also average, visibility data, and UV fits, and in Kazi measurement set format. So this mainly for reference. Slides will be uploaded later, so you can follow these steps in detail. So this is how you can install the pipeline. So you can just git clone the repository. Then in the README, there's a link to a specific Casa version that the pipeline uses. So right now, the pipeline doesn't use the main Casa release. It uses Casa from a specific branch that still has one or two features that are specific and needed for VLBI data processing that hasn't made it yet into the main Casa branch. So this is why the pipeline still uses a special Casa version. But I expect actually for the next major Casa release that this will change, and then all of the VLBI functionality will be in main Casa, and then essentially this step is no longer needed, and you just get your latest Casa version installed, and then the pipeline can make use of that. But now you would just download the special Casa like this and say you have it in your same folder. And then there's just this one setup script that you can run here. You say run it in your working directory. Then it will search for Casa versions that it can link to. Right? So this would then link the pipeline to the one Casa version that you just downloaded. Otherwise, you can also run the script to as soon as with the next Casa update. You can then also point it to your normal Casa installation if you then have the latest one with all of the VLBI functionality. Then you just add the executable to your path, and you add the actual scripts, the modules to your Python path, and then it's ready to go. There is, by default, it uses plotms for diagnostics, but specifically for VLBI data, there's some nicer tools that produce nicer plots so faster. So this is jiveplot software here developed by Jive. So this is optional, but it's highly recommended. So you just have to either you just install jiveplot, or you can also install Singularity, which is actually now Obtainer. And as long as this is then in your path, then it will use the jiveplot or jiveplot through Singularity to produce your visibility data plots instead of using plotms. Also note that also the entire pipeline is also available as a containerized version. So this is needed if you want to run this on a Mac. So otherwise, with this Casa MPI, it only works on Linux. Or if you don't, if you don't even want to follow these installation steps, and it's easier to just get it from containerized version here. You're using Singularity. You can also use Docker. Or if you care really a lot about being system independent and scientific reproducibility, because then you can just download, in this example, would download, let's say, the latest version, but you can also download actually any version from any version of the pipeline. They're all tagged by specific commit IDs. You can look at this website here, and then also pick a specific pipeline from a specific code version. They're all available here, and you can run your calibration with this. And then you can say, well, exactly with these input files and this one container that I used, my results, my going, to get to calibrated data are fully reproducible. So let's now say you have now downloaded the pipeline. Then how you run it is you just create, say, somewhere a clean working directory, and you put links to all of the required data and metadata there. So this would be, obviously, you need your FITS-IDI files. Then you would usually have untap tables, except for bit dependent on which VLBI array you're looking at. VLBA, for example, has these attached to your FITS-IDI files already, so these are then not needed. But for both GMVA and EHT data, you will get separate untap tables together with your data that you can then put in your working directory. For the GMVA, you also get weather data. So this is needed to do later on a correction for atmospheric opacity. So it's only needed for GMVA, not for the EHT, because this was done already at the telescopes. And optionally, if you get these from the correlator, you can have some files that contain selections of bad data that you should flag in a priori way. And your list potentially of known receiver temperatures. So this is then only useful or only needed for the GMVA for this opacity correction fit. So normally, if you do this opacity correction, you need your receiver temperatures. If you don't have a priori information, the code will fit for this. But if you know your receiver temperatures, you can also specify them in a file, and then the code doesn't need to fit for them. And in principle, you can also use models of the sources that are then taken into account for the calibration, but that's not usually something you do in VLBI data processing. But you can. So you can, for example, do first calibration, go all the way to the imaging, and then with your final image model, redo the calibration with the image model already taken into account for fringe fitting and everything else. Okay, so but now let's say we are in our working directory. We've put all of the necessary data there, and then you just copy this template of the input files to your working directory. So let's say you've installed Picard somewhere, and you just go to Picard input template and you copy it to a working directory, and then your working directory will look generally like this. So you have your untap tables, you have, this is now example VN data, actually your FITS IDI files can be one, can be multiple. Maybe you have a flag file, maybe you have a receiver temperature file, maybe you also have a source model, and then your input of the pipeline. And then you set initially just a few parameters in these input files. I'll show you later how this is done. So these are the names that you want for your science targets and your calibrator sources, and the name of the array, so if it's EHT or GMVA, and a list of reference antennas. Usually then ALMA is first, so that's quite easy. And once you've done that, you can just run the pipeline with this one single command. There's also highly flexible command line interface. I'll show you some other examples of things that you can do. For example, you can not do any calibration, but only produce a listops, Casa listops file like this. Or with these steps here, so with this -q, you can always select to only run specific steps. It's, for example, useful if you just want to rerun specific steps of the pipeline. So in this case, this will give you only plots of the uncalibrated data to maybe look at initially before you set any parameters in detail. Or just one other example, you can specify also the number of cores to be run for specific steps, and then here in this case, running only step number 4. And maybe because we'll skip this unless they're very urgent, immediate questions. Otherwise, I need to hurry up a bit to make it in time. Okay, there's still time for questions. So that is generally how you set up the pipeline. Now I'll show you how you do this first for GMVA and then for EHT data. Okay, so this is what we so generally saw before. You go to your working directory. For GMVA, you would have a FITS file, so there's a .fits extension, a weather table, and untap tables. So all of this you get, as George explained, from the correlator. See, you put our input files here, and then we added array.imp, right? And there we just say array type equals GMVA. One of the things that you probably want to do for GMVA data, because sometimes you can have very low SNR baselines. So we want to set this parameter here, fringe exhausted ref unsearched islands true. Okay, it shows already how much you can fine tune the pipeline, but this is recommended for GMVA data. This essentially says if you have subarrays in your data and you can't connect them by fringe fittings, let's say GMVA, you have fringes between all your stations in Europe and all your stations in the US. But no fringes, say, across the Atlantic, then you should set this parameter to true, because then you can treat both as 2 separate subarrays. If you have it to false, the pipeline will say, well, I can't connect all of the fringes in the end, and it would throw away 1/2, or either the European or the US stations. So this you don't want, so you want to set this parameter to true. Then it's also just recommendation how I would run it on GMVA data first with this command over here. because this one will produce just some system temperature plots and raw visibility data plots that you can then inspect, and only then set your list of reference antennas and which sources you want as science targets and which ones you want as calibrators, because then you looked already at the data and know, oh, okay, these antennas and these sources, there the data looks good, so I want to use them as reference antennas and as calibrators. But usually, putting ALMA first, then NOEMA, Effelsberg, GBT, and then Los Alamos and KVN stations. That's typically how this could look like for a big array like the GMVA. And then these are, if you run back and forth here, so if you run this step here, this is typical pipeline output that it produces in terms of the visibility plot on the left and system temperature plot on the right. So visibility plot here, so this is one scan, one baseline, averaged in time, and then your full frequency spectrum over here. And bottom part, this is your amplitude, and then color-coded your correlation product. So this is your RR and LL, so these form Stokes I. And here you have your cross-hands that form lower intensity polarization data. And on top, here you have the phases, and you can see, this is because it's uncalibrated data, you see a multi-band delay. But this, for example, if it looks like this is really good data, and then this is a good source to use as a calibrator, and probably either Fort Davis or Kitt Peak are good reference antennas, because they have a clean signal here that you can use very well for calibration. And then system temperature plots here for specific antennas as a function of time for different sources are shown here. So if everything is working well at the telescope, it will look like this. So you can look at this source, also observed mostly here. Just a nice trend of how system temperature goes with the source elevation here. So this would be a good antenna to pick. And here is St. Croix, for example. This is where you can see that there are problems, and maybe this station you don't want to use as a reference antenna, or potentially even flag some data where suddenly you have these spikes in system temperatures that are in this case here due to bad weather. And then, so after you've set all your inputs, again, this is just setting these things in these simple text files, then you can just run the pipeline with this one single command. So that's for GMVA data. Now for EHT data, you can follow similar steps, but you will need or probably want to set some more specific parameters because EHT data can get quite tricky, and you need to tune the pipeline a little bit to work well, or work as good as it can be. But to help you with that, there's also this additional repository, this CASA EHT repository that you can just download like this. And this has two things. One, it has a wrapper script to call Picard for you on EHT data. And it also has many examples of EHT input configurations that you can look at. Our working directory will now look like this. Right, so you have several folders with your, in this case, it's .fits. So again, fits IDI data. That is just a result, if you remember, with all these individual files. So if you extract them, you'll see many folders with these fits files that you can just put into your working directory or links to it. And then you have one untap table. As I said, this untap table already has opacity corrected system temperature, so you don't need a weather table. And then you can just run, again, copy a version of your input template to your working directory, as we've seen before, and then edit this one locally as needed. And this is shown here. This is a recommendation how you should set pipelines for EHT. So you can see that there are many things now where we're fine-tuning parameters. So this is why you may want to download this CASA EHT repository. Because there all of these parameters are set, but for completeness, if you want to do it from scratch, this is how you can do it. So I'll walk briefly through it. It's an observation.im. Just as an example, you may want to set, okay, my science targets here are M87, Sagittarius star, OJ287. In my track, I know I have good data on 3C279, a bright source, so you set as calibrator. I set EHT as an array. And my reference antenna is again ALMA first, and LMT, NOEMA, Euro 30 meter, and JCMT. As one example here, again, it's best to look at the data and then pick the stations you think work best. And then there's some, fine-tuned parameters that just come, from a lot of experience we have with EHT data and knowing how things work best or better than, using the generic default inputs of the pipeline. So we already know after correlation the size of our residual delay and rate windows, so we can put them in. We know quite well which, for fringe fitting and phase calibration, which ranges of solution intervals for the calibration work well there. So these are also put in here. Then we also know that we can, for EHT data, be a bit more aggressive in our fringe fit signal to noise ratio cutoffs. So the default version of the pipeline is quite conservative, but for EHT, we know we can put them to some lower values. These are just experimentally determined, so you can put these values here. We know that these work well, and you will get still good fringes that are no false detections. And just a few more examples here. We know that we understand very well the noise properties of the EHT, so we know that we need to scale our sigma values just by the small number of 3%. So it's a small effect, but if you want to include it, you can. Then there's this parameter here, which deals a bit about how the pipeline manages memory if you run it on multiple CPU nodes. So EHT data, because of very broad bandwidth and small channelization, actually is very memory intensive. So this parameter here just agrees a little bit to be more conservative with the use of memory, because otherwise you can get into trouble with the pipeline running out of memory. And for example, the EHT has a full digital bandpass. So the individual spectral windows don't actually belong to individual bandpasses of the station. So we want to turn off our edge channel flagging, because otherwise we would actually flag edge channels in the middle of our true actual bandpass. Then after these inputs are set, you can again run the pipeline just like this, or you can use this special process EHT script that is from this Kazi EHT repository, and I had there an earlier slide, which does a few special tricks to help you with the processing of this very heavy EHT datasets. Right, that one EHT dataset can be up to 1 terabyte in size, for example, and fringe fitting is quite memory intensive. So this, if you just run the pipeline like this, you can run into trouble. But this process EHT script is a bit more careful in balancing the number of CPU cores for individual steps of the pipeline versus how much memory these individual steps need. And it does one other thing that I just want to mention here. It's a question of philosophy, and that is how you treat your science target versus your calibrators. So the normal VLBI run, how you run the pipeline normally, is that it uses the calibrators mainly to get to your instrumental calibration, and then it does, say, the best perfect deep fringe fit calibration on your science target. So that assumes that your calibrators you would only maybe use as check sources, but you don't want to do science on it. This script, you would assume that all of the sources, including your calibrators, for example, 3C279 that we set previously, you want to do science on it and you want to obtain the best possible calibration. So this will actually then run Picard in 2 steps. First up to all instrumental calibrations, then it will change, let's say, the input to then change all sources. So relabel them as calibrator sources in the input, as science targets in the input, and then run the remaining deep fringe fit steps on all of the sources and not just on the ones that you specified as science targets in the beginning. This may also be useful for GMVA or other data sets. So here I put the steps down here that are being essentially run by this process EHT script. So, for example, if you want to do this in the GMVA run, you can do this by first running Picard, selecting only these steps, running steps 0 to 10. Right? Then you did all the instrumental calibration steps. Then you would remove these intermediate products, and then you change your input at this stage to just setting all your calibrator sources to none. Maybe before you had 3C279, and then adding 3C279 to your list of science targets, and then running the remaining steps of the pipeline. So this does 0 to 10, and this one does, and the remaining ones 11 to some high number. I think you stop at the highest that it can do, which is maybe step 17 or so. Okay, let me quickly check. So this was the main thing I wanted to talk about. These were all actually the mechanical steps of how you can set up the pipeline, how you can get the data, and how you can get to calibrated data. I had a few more slides, actually in a bit more detail, but it's also very VLBI specific, of, let's say, some diagnostics that the pipeline produces and how you can interpret them. I just was told that I'm out of time, so I'll skip this optional part, and maybe we then go to here to the questions, and then if there are questions about this, I can still show some slides on that if needed. So thanks all.